To begin our journey into understanding the universe and its expansion, it's vital to first set the stage by contemplating the immense cosmic scale that surrounds us and acknowledging our unique place within it. When we gaze up at the night sky, we're presented with a tapestry of stars that, at first glance, seems infinite and dazzlingly complex. Yet, these points of light are merely the beginning. A small window into a universe of staggering proportions and depths that challenge the very limits of human comprehension. Imagine standing on a small hill on Earth, looking up at the night sky. Each star you see is not just a pinprick of light, but a blazing sun, many of them far larger and more luminous than our own. The nearest stars are light years away, a distance so vast that light itself, traveling at an incredible speed of approximately 300,000 kilometers per second, takes years to journey from these stars to our eyes. A light year, then, is not a measure of time, but a unit of distance that helps us grasp the immensity of space. Our home is the planet Earth, a modest sphere orbiting an average star, the Sun, which is one of hundreds of billions in our galaxy, known as the Milky Way. The Milky Way itself is an enormous spiral galaxy filled with countless stars, star clusters, nebulae, and cosmic dust. It spans roughly 100,000 light-years across, which means light takes 100,000 years to travel from one side of the galaxy to the other. But even the Milky Way is only a speck in the vast ocean of the universe. Galaxies themselves cluster in groups and superclusters, massive assemblies made up of thousands of galaxies, stretching hundreds of millions of light-years. These structures form an intricate cosmic web, with filaments of galaxies and vast voids that extend across billions of light-years. The observable universe, that portion of the universe from which light has had time to reach Earth since the beginning of the cosmic expansion, measures roughly 93 billion light-years in diameter. This estimate grows as time passes because light from more distant places finally arrives, giving us a deeper look back into the cosmos's history. Yet, despite this incomprehensible grandeur, humans and our planet are infinitesimally small in the cosmic context. Our entire biosphere, the cradle of human civilization, is but a grain of cosmic dust compared to the expanses that stretch beyond our night sky. Yet, paradoxically, it is from this small vantage point that we have learned so much about the universe, developing powerful telescopes, space probes, and theoretical frameworks that allow us to unravel mysteries billions of light-years away. This perspective, understanding the universe's vastness and our place within it, is not merely an exercise in awe. It is foundational for grasping the nature of the cosmos, particularly when we explore the concept of expansion. The notion that the universe itself is stretching and evolving over time introduces profound questions that ripple through cosmology, physics, and philosophy. From the ancient stargazers who saw celestial spheres turning overhead, to modern scientists detecting faint cosmic signals billions of years old, humanity's attempt to map the universe's scale has evolved dramatically. Today, our spacefaring missions and super-sensitive instruments peer deep into space and time, extending our cosmic horizon ever further. In moving forward, it becomes clear that to understand what it truly means for the universe to be expanding, we must first appreciate the extraordinary magnitudes involved. This sets the stage for a deeper inquiry into space, time, and the fabric of reality itself. As we continue, we will embark from this vantage point, our tiny but remarkable place within an immense cosmos, to explore the ideas that have shaped human understanding of the universe across ages. This journey will peel back layers of cosmic mystery and illuminate how humanity came to comprehend, in the last century, that space itself is stretching like a balloon inflating, raising the question, What exactly is the universe expanding into? Now that we have taken a moment to comprehend our cosmic scale and humanity's role within it, we can travel back through time to glimpse how our ancestors first tried to explain the heavens. From myth to science, these ancient cosmologies laid the foundation for all future explorations. So let us turn the page and explore those early human conceptions of the cosmos, where wonder and curiosity first sparked an enduring quest to understand the universe. Long before the advent of modern telescopes and scientific methods, early humans looked up at the night sky with a mixture of wonder, curiosity, and reverence. These distant ancestors, living tens of thousands of years ago, wove the stars, the moon, and the sun into rich tapestries of stories and myths that sought to explain their origins, movements, and significance. These early cosmologies, early conceptions of the cosmos, served as the foundation upon which later scientific explorations would build, and they reveal how deeply intertwined humanity's quest for knowledge has always been with its need for meaning and narrative. At its core, ancient cosmology was an attempt to grapple with the mysteries of existence, to situate human life within a grander cosmic order, and to find patterns in the ever-moving sky. In the absence of scientific instruments, these early cultures used observation, intuition, and imagination to piece together explanations about the nature of the world and the universe beyond. Many ancient societies shared strikingly similar cosmological themes, despite vast geographical distances and cultural differences. A common belief was that the universe was a finite, often layered structure, composed of heavens above and an underworld below, with the earth suspended somewhere in the middle. The sky was often viewed as a solid dome or canopy, painted with stars and celestial bodies. This concept of a firmament or celestial sphere features prominently in the cosmologies of the Babylonians, Egyptians, and Greeks. For example, the Babylonians, one of the earliest civilizations to systematically study the sky, constructed detailed star charts and celestial calendars. Their worldview divided the cosmos into distinct realms: Earth, the heavens, and the underworld. They saw the gods as controllers of these realms and attributed heavenly events, such as eclipses or planetary movements, to divine actions. This blend of astronomy and mythology laid crucial groundwork for future astronomical inquiry. In ancient Egypt, cosmology was deeply spiritual and symbolic. The sky was often personified by the goddess Nut, arching over the earth god Geb. The daily rising and setting of the sun were interpreted as manifestations of these deities' eternal dance, a cycle representing rebirth and order from chaos. Egyptian cosmology also informed their sophisticated calendars and timing of religious rituals, reflecting an intimate link between celestial phenomena and human affairs. Moving to the ancient Greeks, their cosmologies evolved from mythological origins into more systematic philosophies about the universe's nature. Early thinkers such as Hesiod described the cosmos as emerging from primal chaos, with personified deities representing celestial features. Yet, over time, Greek philosophers sought to explain celestial motions through reason and observation rather than myth alone. One of the most influential early Greek ideas was the geocentric model, which placed Earth at the center of the universe. In this view, the sun, moon, planets, and stars were embedded in concentric spheres that revolved around the unmoving Earth. This idea was formalized by figures like Plato and Aristotle, who believed in a perfect, unchanging cosmos composed of crystalline spheres. Aristotle's cosmology was deeply entwined with his physics and metaphysics, positing a universe that was finite in extent, spherical in shape, and hierarchical in composition. This geocentric concept resonated powerfully for centuries, becoming the foundation of Western astronomy and cosmology well into the Middle Ages. It was not merely a scientific model, but also a worldview aligned with philosophical, religious, and cultural ideas about humanity's privileged status in creation. However, even within these frameworks, there was curiosity and speculation beyond the visible sky. Some ancient thinkers, such as the atomists Leucippus and Democritus, imagined an infinite universe filled with countless worlds, challenging finite cosmologies. These ideas, though marginalized for a time, paved the way for future scientific revolutions. Farther east, ancient Indian cosmology presented its own unique visions of the cosmos. Rooted in Vedic traditions, Indian conceptions described an enormously cyclic universe with vast spans of time called kalpas. The universe was viewed as endlessly created, destroyed, and reborn in rhythmic cycles. Many layers of reality and numerous worlds coexisted, embedded within an expansive cosmic order overseen by deities such as Brahma, Vishnu, and Shiva. India's Jain and Buddhist cosmologies also contributed intricate descriptions of cosmic structure and the nature of existence beyond the physical plane. Similarly, Chinese cosmology revolved around balancing cosmic principles such as yin and yang, as well as the interplay of the five elements. The heavens were conceived as a vast dome, with the earth flat or square beneath it. The celestial movements were tied to the cycles of time and the mandate of heaven, linking cosmic harmony with social order. What stands out across these diverse ancient cosmologies is the profound human instinct to seek order in the cosmos. Without modern instruments, early humans relied on careful observation, tracking the rising and setting of stars, lunar phases, and solar patterns to build calendars essential for agriculture, navigation, and ritual. These observations were interwoven with storytelling, religion, and philosophy, creating rich tapestries that offered meaning and a sense of place in an immense and mysterious universe. Interestingly, many of the ideas birthed in ancient cosmologies laid conceptual seeds for later breakthroughs. The recognition of celestial regularities invited a search for underlying laws. The notion of layers or spheres of heavens introduced geometric thinking about space, and the debates over Earth's position and finiteness foreshadowed fundamental shifts during the scientific revolution. Reflecting on these early human conceptions reminds us that our modern understanding, complex though it may be, is built upon millennia of thought, observation, imagination, and curiosity. Every ancient myth, every philosophical speculation, was a stepping stone on the path toward our current grasp of the cosmos. As we move forward in this exploration, the next chapter will examine how the views from Aristotle to Copernicus transformed our perspective of space and the universe. The shift from an Earth-centered cosmos to a sun-centered one not only altered astronomy, but also revolutionized humanity's place in the universe, setting the stage for the modern age of cosmic discovery. But before we arrive there, let us pause to appreciate this vast history of human inquiry, a testament to our desire to understand the sky above and our place beneath the stars. As we transition from the rich tapestry of ancient cosmologies, we find ourselves entering a transformative epoch in the human understanding of the cosmos, an era marked by profound shifts in perspective, driven by the ideas of thinkers like Aristotle and later Nicholas Copernicus. This period, stretching over many centuries, set the stage for the eventual overthrow of Earth-centered models and laid the foundation for the modern scientific revolution. Aristotle, the towering intellectual force of the 4th century BCE, synthesized much of the philosophical and scientific knowledge of his time into a cohesive worldview which would dominate Western thought for well over a millennium. His vision of the cosmos was both comprehensive and elegant, one that married observation with philosophy and mathematics. At the heart of Aristotle's cosmology was the geocentric model, a universe centered around a stationary Earth. Aristotle proposed a finite, spherical cosmos consisting of nested, concentric celestial spheres. Earth sat immobile at the center, surrounded by the spheres bearing the moon, sun, planets, and stars. These spheres carried celestial bodies in perfect circular motion, the embodiment of perfection and unchanging eternity. The very heavens, in Aristotle's conception, were composed of a fifth element, ether, different in nature from the four terrestrial elements of earth, water, air, and fire. This conception was deeply intertwined with Aristotle's physics. He posited that the earth was the natural resting place for the heavier elements, earth and water. Hence, it remained still at the center, while the lighter elements naturally sought the heavens. This elegantly explained why we see the earth as immovable and why celestial objects moved in regular, predictable ways. Although ingenious for its time, Aristotle's model contained limitations. It assumed a static universe with perfect symmetry and circular orbits, ideas that would later be challenged by observations. Nevertheless, his influence was profound, permeating medieval scholasticism and becoming the official cosmological doctrine of Christian Europe. His ideas fused with theological assumptions, reinforcing the notion of a hierarchical, purpose-driven cosmos with humanity at its pinnacle. Yet, long before the Renaissance, certain thinkers began questioning the entrenched geocentric worldview. Ptolemy, a second-century astronomer and geographer, refined the Aristotelian model to better fit observations by introducing epicycles, small circular motions superimposed on the larger planetary orbits. With this complex machinery, Ptolemy preserved the Earth-centered cosmos and circular motions, but at the cost of increasing intricacy and less elegance. Fast forward to the Renaissance, socio-cultural and intellectual currents set the scene for a seismic shift in cosmology. The rediscovery of ancient Greek texts, combined with advancements in mathematics and the printing press's proliferation of knowledge, ignited curiosity. Astronomers and philosophers began experimenting with alternative models that addressed inconsistencies in the geocentric framework. Among these visionaries was Nicholas Copernicus, a Polish mathematician and cleric born in the late 15th century. His groundbreaking work, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, published in 1543, proposed a heliocentric model of the universe. The Sun, not the Earth, occupied the center, while Earth and the other planets orbited around it. Copernicus did not discard all classical ideas. He preserved the belief in uniform circular motion and the perfection of celestial spheres. However, by positioning the Sun at the center, he offered a more straightforward explanation for planetary motions, especially the apparent retrograde motion, where planets sometimes appear to move backward in the sky. This paradigm shift was radical. By demoting Earth from its privileged cosmic throne, Copernicus challenged philosophical and theological assumptions. The Earth was no longer unique or stationary. It was a planet among others in motion. Such a revelation provoked discomfort among religious authorities and scholars adhering to Aristotelian doctrine. Despite its revolutionary nature, Copernicus's model did not immediately overthrow the geocentric worldview. The model, although mathematically simpler in some respects, still relied heavily on circular orbits and epicycles to fit observations. Moreover, it lacked direct empirical proof at the time, making its acceptance gradual and contentious. Following Copernicus, other astronomers such as Tycho Brahe sought hybrid models, and Johannes Kepler would later dramatically refine planetary trajectories with his discoveries that orbits are elliptical, not circular. Galileo Galilei's telescopic observations of Jupiter's moons and the phases of Venus provided concrete evidence supporting heliocentrism. This slowly evolving understanding marked a profound change in human consciousness about space. The universe was expanding not only in physical terms, but metaphorically, as humanity began to see itself as part of a dynamic and immense cosmos rather than its fixed center. The transition from Aristotle to Copernicus thus represents a critical juncture where observation, reason, and courageous questioning shattered old paradigms. It reminds us that the story of our cosmic understanding is a human saga of bold ideas challenging comfortable certainties. As we prepare to delve deeper into the birth of modern astronomy and how the idea of an infinite universe took hold, remember this pivotal transformation, a turning point that redirected our gaze away from Earth's fixed vantage to the broader celestial dance, ultimately leading us toward the awe-inspiring concept that the universe itself is expanding into something far greater than previously imagined. As we progress from the seismic shifts that marked the transition from ancient geocentric models to the heliocentric universe proposed by Copernicus, we arrive at a pivotal era often considered the birth of modern astronomy. This epoch not only revolutionized our understanding of the heavens, but also planted the profound idea of an infinite universe, an idea that would cast away millennia-old assumptions of a finite cosmos and usher humanity into a new realm of cosmic imagination. The 16th and 17th centuries, known as the Renaissance and the Scientific Revolution, were crucibles of intellectual brilliance. The cumulative works of figures such as Nicholas Copernicus, Johannes Kepler, Galileo Galilei, and later Isaac Newton redefined astronomy from a philosophical and theological pursuit into a rigorous empirical science grounded in observation, mathematics, and the laws of physics. Copernicus's heliocentric model destabilized the Earth-centered paradigm, yet it retained the classical notion of perfect circular orbits and celestial spheres. It was Johannes Kepler who, building upon meticulous planetary observations made by Tycho Brahe, refined this understanding drastically. Kepler identified that planetary orbits are not perfect circles, but ellipses, with the Sun situated at one focus of the ellipse. This discovery, articulated in his three famous laws of planetary motion, dismantled the long-held dogma of celestial perfection and introduced a more precise mathematical framework to predict planetary positions. Around the same time, Galileo's improvements to the telescope unveiled new cosmic realities. He observed moons orbiting Jupiter, mountains and craters on the Moon, phases of Venus, and spots on the Sun. These discoveries not only challenged Aristotelian cosmology, but also provided tangible proof that heavenly bodies were physical objects subject to change, similar in nature to Earth. His findings ignited intense debates with lasting cultural and religious implications, but they undeniably grounded astronomy in empirical data. Isaac Newton, arriving at the dawn of the 18th century, unified the motion of celestial and terrestrial bodies under universal laws of gravitation and motion outlined in his landmark work, Principia Mathematica. Newton's laws not only explained Kepler's planetary orbits, but also integrated the heavens into a coherent system governed by universal principles expressed through mathematics. This was a monumental leap, for it replaced mysticism and circular logic with predictive, testable theory. With these advancements, the idea of the cosmos expanded beyond templates of spheres and finite boundaries. Yet, the question of whether the universe itself was infinite remained both scientifically elusive and philosophically profound. The concept of an infinite universe gained traction as astronomers grappled with the immense scales involved and the discovery of countless stars strewn across the night sky. Prior notions of a closed, finite cosmos were challenged by observations revealing the staggering number of stars and their distributions. If the universe contained innumerable stars stretching without known bounds, it hinted at an infinite expanse. Moreover, philosophical reflections played a crucial role. If the universe was finite, what lay beyond its boundary? And would a boundary not imply an edge or an outside? Questions fraught with metaphysical tension. The infinite was conceived not merely in spatial terms, but also temporally, as many thinkers began to entertain the idea of an eternal universe without beginning or end. Yet, infinite universes posed paradoxes. One such is the Olbers paradox, named after the German astronomer Heinrich Wilhelm Olbers, who in the early 19th century pondered why the night sky is dark if stars are infinitely distributed. If the universe were eternal, infinite, and uniformly filled with stars, every line of sight should eventually end on a star's surface, rendering the night sky ablaze with light. Its darkness suggested gaps in this model, inviting questions about the universe's age, structure, and dynamics. Further, as telescopes advanced, astronomers like William Herschel tried to map the distribution of stars and nebulae, believing these nebulae were distant, fuzzy objects within the Milky Way. However, the very nature of these nebulae sparked debates about whether the universe was limited to the island universe of the Milky Way or far grander. These questions set the stage for the 20th century's breakthroughs. As the edge of the observable universe extended with technological progress, astronomers began to realize the cosmos was far larger and more mysterious than ever imagined. It was the convergence of observation, theory, and mathematics during the birth of modern astronomy that transformed our view from a finite, orderly system to one where the universe might be unbounded and possibly infinite. This reshaped not only science, but also humanity's philosophical outlook. From a cosmos with a defined enclosure placing humankind at the center, to a vast, deep, and potentially endless expanse where Earth and its inhabitants are but one tiny part. This profound evolution in cosmic understanding, rooted in the rigorous probing of the heavens, leads us directly into the next chapter of our story, the groundbreaking discoveries of Edwin Hubble. His observations in the 1920s would confirm that the universe is not static, but dynamically expanding, sparking a new era in cosmology and raising the question that guides our entire exploration. What exactly is the universe expanding into? Before we explore Hubble's discovery and the expanding universe it revealed, it is crucial to grasp how the foundational ideas of modern astronomy and the concept of an infinite universe emerged. Because without this understanding, the magnitude of the expansion and its implications would be almost impossible to comprehend. The early decades of the 20th century stand as one of the most transformative eras in the history of science, especially in the field of cosmology. The universe, long thought by most astronomers to be static and unchanging, was about to reveal itself as dynamic and expanding, thanks in large part to the groundbreaking work of Edwin Hubble. His discoveries not only changed our understanding of the cosmic landscape, but profoundly altered humanity's conception of its place within the vastness of space and time. Before exploring Hubble's contributions, it's important to appreciate the scientific context of the period. Up until the early 1900s, the prevailing view among many astronomers was that our Milky Way galaxy constituted the entire universe. While the galaxy contained hundreds of billions of stars, it was considered a solitary island drifting alone in an otherwise empty expanse. The glowing nebulae observed in the night sky were often thought to be cloud-like gas formations within the Milky Way itself. However, this picture was beginning to crumble. Throughout the late 19th and early 20th centuries, improved telescopes allowed astronomers to peer into these nebulous objects with unprecedented clarity. The question emerged: were these nebulae distant star systems like our own galaxy, or inherently different phenomena? Enter Edwin Hubble, an American astronomer armed with one of the era's most powerful instruments, the 100-inch, 2.5-meter Hooker telescope atop Mount Wilson Observatory in California. In the 1920s, Hubble dedicated himself to studying a set of specific nebulae, including the Andromeda Nebula, now known as the Andromeda Galaxy, aiming to unlock fundamental mysteries of cosmic scale. By analyzing distinct variable stars known as Cepheid variables within these nebulae, Hubble utilized a crucial tool developed earlier by Henrietta Swan Leavitt. The regular pulsations of Cepheids correlate directly with their intrinsic brightness, making them cosmic standard candles. By comparing a Cepheid's measured brightness to its actual luminosity, Hubble was able to calculate its distance with reasonable precision. The results were staggering. Some of these nebulae were far too distant to be part of the Milky Way, lying millions of light-years away. This revelation confirmed that the universe consisted of countless galaxies, making the Milky Way just one island in a vast cosmic ocean. The scale of the universe instantly multiplied beyond what most had imagined. Yet Hubble's most profound discovery was still unfolding. As he measured the light spectra from these galaxies, Hubble noticed a systematic shift towards the red end of the spectrum. This phenomenon, termed the redshift, indicated that the galaxies were moving away from Earth. But even more intriguing was the correlation between distance and velocity. More distant galaxies showed greater redshifts, implying faster recessional speeds. This observation led to what we now call Hubble's law. The recessional velocity of a galaxy is directly proportional to its distance from us. In simple terms, the farther away a galaxy is, the faster it recedes. Imagine dots on a balloon's surface that move away from each other as the balloon inflates. Similarly, galaxies appear to be receding from one another as space itself expands. The profound implication was that the universe was not static, but expanding. This discovery overturned centuries of scientific consensus and was the first empirical evidence that the cosmos was dynamic and evolving. It suggested that space itself was stretching, carrying galaxies along like raisins in a rising loaf of bread. The recognition of the universe's expansion had a profound impact beyond astronomy. It provided a crucial piece of evidence for emerging models of cosmology, including the revolutionary Big Bang theory, which posited that the universe began as an extremely hot, dense point and has been expanding ever since. Hubble's findings were met with varying degrees of acceptance. While some scientists embraced the new cosmology enthusiastically, others found it philosophically challenging. The idea that space itself was growing suggested a universe with a beginning, a concept that raised deep questions not only scientifically, but also metaphysically. Nonetheless, Hubble's work laid the foundation for much of modern cosmology. His measurements continue to be refined with new technologies, and what began as an observation of a few galaxies blossomed into a comprehensive understanding of cosmic expansion, dark energy, and the ultimate fate of the universe. Understanding Hubble's discovery provides an essential key for subsequent topics, such as the detailed nature of redshift, the Big Bang model, and the fabric of spacetime. It guides us toward grappling with one of the most profound inquiries in all of science. When we say the universe is expanding, what exactly is expanding, and into what? As we continue, we will delve deeper into the phenomena of redshift and the increasingly compelling evidence that underpin the expanding universe framework, uncovering the behaviors of light and space that subtly yet decisively reveal the grand architecture of our cosmos. As we continue our exploration into the cosmos and the profound question of what the universe is expanding into, it becomes essential to delve into one of the most critical phenomena underlying this understanding: redshift. The discovery and interpretation of redshift provide some of the most compelling evidence that the universe is not static, but expanding. To truly grasp what redshift reveals, we must examine what it is, how it works, and why it fundamentally altered our cosmic worldview. At its simplest, redshift refers to the observation that light or other electromagnetic radiation from an object is shifted toward the longer wavelengths, or the red end of the spectrum, when observed from a distance. But to understand why this phenomenon is significant, it helps to break down the nature of light and its interaction with motion. Light behaves both as a particle and a wave. The wave aspect is characterized by its wavelength and frequency. Blue light has shorter wavelengths and higher frequency, whereas red light has longer wavelengths and lower frequency. When a luminous object moves relative to us, the waves of light it emits can appear compressed or stretched due to the Doppler effect, the same principle that causes the pitch of a passing ambulance siren to change as it speeds past. When an object moves toward us, the light waves get compressed, shifting towards the blue end of the spectrum. This is called blue shift. Conversely, when an object moves away from us, the waves are stretched, resulting in a red shift. By measuring this shift, astronomers can determine how fast an object, such as a distant galaxy, is receding from Earth. In the early 20th century, astronomers like Vesto Slipher began to measure the spectral lines of distant nebulae, discovering that many exhibited redshifts, suggesting they were moving away. Edwin Hubble built upon these measurements, revealing the crucial relationship between redshift and distance, known today as Hubble's law. This law states that the velocity at which a galaxy recedes from us is directly proportional to its distance, implying a uniform expansion of space itself. It's vital to note that the redshift observed in galaxies is not solely a Doppler effect caused by objects moving through space, but is largely due to the expansion of space itself. This distinction is subtle but important. Instead of galaxies racing away through static space, the fabric of space itself stretches, increasing the distance between galaxies. As space expands, the light traveling through it also stretches, increasing its wavelength, which manifests as redshift. Redshift measurements extend far beyond just nearby galaxies. Observations using powerful telescopes and satellites detect redshifts in extremely distant galaxies and quasars, some so far that their light has traveled billions of years before reaching us. The greater the redshift, the farther away, and thus the older, the object is in terms of cosmic history. This relationship allows astronomers to peer backward in time, observing the early universe and tracking how galaxies and cosmic structures formed and evolved. Redshift has thus become an indispensable tool not only for measuring cosmic distances, but also for mapping the universe's expansion history. Moreover, detailed measurements of redshift underpin key cosmological models, including the Big Bang theory and the accelerated expansion attributed to dark energy. The observation that galaxies at the largest scales exhibit higher than expected redshifts implied that not only is the universe expanding, but this expansion is speeding up, a discovery awarded the Nobel Prize in Physics in 2011. Understanding redshift also brings into focus important nuances to avoid common misconceptions. The expansion of the universe is not like an explosion with galaxies flying outward into empty space. Rather, it's an intrinsic expansion of space itself, meaning that distant galaxies' light shifts in wavelength because the space through which it travels is stretching. Furthermore, some objects appear to have recession velocities greater than the speed of light due to this space expansion, an outcome perfectly consistent with Einstein's theory of relativity because it is space itself that expands, not objects moving within space. The evidence gleaned from redshifts has been accumulated from a variety of observational campaigns, from ground-based observatories mapping vast swaths of galaxies to space telescopes studying the cosmic microwave background radiation, the afterglow of the Big Bang, which itself exhibits a telltale redshift corresponding to the universe's cool and expanding state. In summary, redshift stands as a cornerstone of observational cosmology. It beautifully encapsulates the dynamic nature of the cosmos, revealing that the universe is not a fixed, eternal arena, but a living, growing entity. The interpretation of redshift as a sign of cosmic expansion invites us to reconsider what space truly is and poses deeper questions about the universe's shape, extent, and ultimate fate. As we proceed, we will delve into how this expansion is framed within the Big Bang model, tracing the origins and development of our understanding of universal expansion and exploring what such a dynamic cosmos implies about the profound question of what the universe might be expanding into. Our journey through the cosmos now brings us to a foundational chapter in modern cosmology. The Big Bang model, its origins, its development, and its pivotal role in shaping our understanding of the universe's expansion. This model is more than a scientific theory. It is a grand narrative that offers profound insight into the universe's beginning, inhabiting the intersection of observation, theoretical physics, and philosophical reflection. The story begins in the early 20th century, a time of remarkable discoveries and shifting paradigms. Building on Einstein's revolutionary theory of general relativity, which described gravity as the curvature of spacetime caused by mass and energy, scientists realized that the cosmos could be dynamic rather than static. However, Einstein himself initially resisted the idea of a changing universe, introducing the cosmological constant to preserve a static cosmic model. In the 1920s, astronomers such as Edwin Hubble observed that distant galaxies are moving away from us with velocity proportional to their distance, implying an expanding universe. This empirical evidence challenged the long-standing static universe concept and inspired theorists to explore what an expanding spacetime means for the cosmos's history. Building on these findings, the Belgian priest and physicist Georges Lemaitre proposed in 1927 what he called the hypothesis of the primeval atom, the idea that the universe began as a single, incredibly dense point that underwent rapid expansion. Lemaitre's work integrated general relativity with observational data, suggesting not only expansion, but a definite cosmic beginning. Though initially met with skepticism, this concept gradually gained traction. Further development came from Russian physicist Alexander Friedmann, who in the early 1920s formulated solutions to Einstein's field equations, allowing for expanding or contracting universes. Friedmann's mathematical models demonstrated that a dynamic universe was a natural consequence of general relativity without the need for the cosmological constant. The term Big Bang itself was coined somewhat derisively by astrophysicist Fred Hoyle during a 1949 radio broadcast. Hoyle was a proponent of a competing steady-state model, positing an eternal and unchanging universe. Despite his intent to mock, the name stuck, and the Big Bang theory gradually emerged as the most widely accepted cosmological model. Crucial observational support arrived in 1965 with the discovery of the cosmic microwave background, CMB radiation, by Arno Penzias and Robert Wilson. This faint, uniform glow of microwave radiation permeating the universe was predicted to be the residual heat left over from the universe's hot and dense early state. The CMB became a cornerstone piece of evidence validating the Big Bang model, confirming that the universe was once in a much hotter, denser phase. The Big Bang framework, therefore, depicts an evolving universe that started approximately 13.8 billion years ago from an extremely hot, dense state. From that initial explosion of energy and matter, space itself began expanding and cooling, allowing subatomic particles to form, followed by atoms, stars, galaxies, and eventually the large-scale cosmic structures we observe today. The model describes key phases in cosmic history: an initial rapid inflationary period where the universe expanded exponentially in fractions of a second, subsequent nucleosynthesis forming the light elements like hydrogen and helium, and later galaxy formation and development shaped by gravity and dark matter. Mathematically sophisticated but grounded in physical observations, the Big Bang model elegantly accounts for the expanding universe evidenced by redshift, the CMB, and the observed abundance of light elements. Yet, it also leaves open profound questions about what preceded the Big Bang, what drives the current acceleration of cosmic expansion, and the ultimate fate of the universe. By placing the universe's expansion within a contextual narrative, from a dense singularity to the immense cosmos we inhabit, the Big Bang model reshaped scientific and philosophical thought. It moved us away from ideas of a timeless cosmos toward a temporally dynamic one, inviting us to consider beginnings, evolution, and eventual destinies on the grandest scales imaginable. As we advance further, armed with this understanding of the Big Bang, we will examine how astronomers define the universe itself, distinguishing the observable universe from the entire cosmos, and explore deeper physical constructs like spacetime that provide the scaffolding for expansion. These insights will help illuminate the profound question that guides our inquiry. Into what is the universe expanding? As we delve deeper into the mysteries of the cosmos and the nature of its expansion, it becomes critically important to clearly define what we mean by the universe. This may seem straightforward at first, the universe as everything that exists. But in the realms of cosmology and astrophysics, this definition splits into distinct categories that fundamentally affect our understanding: the observable universe and the universe in its entirety. The observable universe is the portion of the cosmos from which light and other signals have had enough time to reach us since the Big Bang nearly 13.8 billion years ago. Because light travels at a finite speed, approximately 299,792 kilometers per second, there is a limit to how far we can see. This cosmic horizon defines our observational boundary, beyond which signals have not yet reached Earth and thus remain inaccessible to our telescopes and instruments. To appreciate the scale of the observable universe, imagine looking out into space and realizing that you are seeing not just distant objects, but essentially time machines. The farther we look, the further back in time we see, witnessing galaxies as they were billions of years ago. The observable universe is roughly 93 billion light-years in diameter, larger than the simple multiplication of the speed of light, and the universe's age suggests, because the expansion of space itself stretches the distance. Light travels over cosmic time. Yet, the observable universe is only a fraction of the total cosmos. The universe in its entirety may be vastly larger, potentially infinite, or it may possess a complex geometric topology that we do not yet fully grasp. This distinction is profound. The universe beyond our observational horizon could host regions of space and structures forever inaccessible to us, beyond light's reach due to the universe's ongoing expansion. Modern cosmology embraces this distinction by adopting models that describe the entirety of the universe in mathematical terms. These models often assume homogeneity and isotropy at large scales, meaning the universe is roughly uniform and looks the same in every direction when viewed on sufficiently vast scales. This assumption underpins the cosmological principle, foundational for cosmological theories. However, the inability to observe beyond our horizon poses inherent limits on what can be empirically known. While we can extrapolate and theorize, the unobservable universe remains, for now, a domain of speculation based on physical laws and mathematical elegance rather than direct evidence. Moreover, the relationship between observable and entire universes becomes even more intricate when accounting for cosmic inflation, a rapid exponential expansion in the universe's earliest moments. Inflation suggests that our observable universe is a tiny patch of an immensely larger cosmos, potentially stretching infinitely outward. The observable sphere is like a bubble within a boundless sea, hinting at the universe's vastness beyond measure. This distinction influences how we interpret the universe's expansion. When cosmologists say, "the universe is expanding," they refer primarily to the expansion within the observable limits, the dynamic growth of distances between galaxies and clusters within our detectable horizon. Meanwhile, whether the entire universe is expanding in the same way and what its global structure is, remain open questions, fascinating and profound. Additionally, the observable universe's finite scope shapes our understanding of time and causality. Events beyond this boundary cannot affect us presently or in the future. Light and other signals have simply not had time to arrive. This cosmic limit introduces horizons analogous to those of a black hole, defining causal boundaries within the universe. To summarize, the universe we can observe and study is a vast, dynamic structure, stretching over tens of billions of light-years and evolving over billions of years. But it is, in a cosmic sense, only a window into a potentially much grander, possibly infinite totality. This distinction between the observable and entire universe not only frames our scientific endeavor, but also humbles us before the immense expanse of existence. As we continue our exploration, this understanding of scale and limitation will be essential. It prepares us to consider how space and time themselves are woven into the fabric of the universe, a fabric that stretches and expands, often in ways that challenge our intuition. Our next step will be to unfold the nature of spacetime as modern physics reveals it, setting the ground for deeper insight into how the universe expands and what that implies about our cosmic reality. To fully grasp the nature of the universe's expansion and to appreciate the puzzling question of what the universe is expanding into, we must first understand the very fabric that underpins reality: spacetime. This concept, born from Albert Einstein's revolutionary theories of relativity, redefined our notions of space and time not as separate and absolute entities, but as interconnected and dynamic features of the cosmos. This profound shift laid the groundwork for modern cosmology and transformed how scientists perceive the universe itself. Before Einstein's works in the early 20th century, space and time were regarded as fixed and independent backgrounds against which physical events unfolded. Newtonian physics treated time as universal and absolute, flowing uniformly for all observers, while space was a static, three-dimensional stage where matter moved and interacted. However, growing anomalies in understanding gravitational phenomena and the behavior of light underpinned the need for a deeper, more unified framework. Einstein's special theory of relativity, published in 1905, dismantled classical assumptions about time and simultaneity. It revealed that measurements of time and space are relative, dependent on the observer's state of motion. For instance, time can dilate, and lengths can contract depending on how fast an observer moves, approaching the speed of light. Yet, special relativity dealt primarily with inertial frames, situations without acceleration or gravity. The more groundbreaking leap came with Einstein's general theory of relativity in 1915. This framework provided a new understanding of gravity not as a force acting at a distance, as Newton conceived, but as the warping or curvature of spacetime caused by mass and energy. According to this theory, massive objects like stars and planets distort the surrounding fabric of spacetime, much like a heavy ball placed on a stretched rubber sheet. Objects follow the curved pathways dictated by this distortion, resulting in what we perceive as gravitational attraction. Viewing gravity as geometry allowed Einstein to describe the cosmos in novel terms. Space and time are woven together in a four-dimensional manifold called spacetime. Events are located not just by spatial coordinates, but also by a time coordinate, and this four-dimensional fabric is dynamic, capable of bending, stretching, and evolving. This realization was transformative for cosmology. It meant the universe itself was not a static backdrop, but a living entity whose geometry could evolve. Einstein's equations describe how mass-energy contents influence the shape and evolution of spacetime on cosmic scales. An immediate consequence of this dynamic geometry is that the universe could expand, contract, or change in complex ways. Indeed, mathematical solutions to Einstein's field equations predicted expanding or contracting universes long before it was observed. Early on, Einstein introduced the cosmological constant in an attempt to maintain a static universe, only to later recognize that the universe's expansion was a natural feature of his theory. One of the remarkable aspects of general relativity is that it precludes the existence of a universal clock or absolute spatial framework. Instead, different observers might slice spacetime differently, and the concepts of distance and time can vary, depending on one's position and motion within the cosmic fabric. Another key insight is that spacetime can be curved in ways beyond simple three-dimensional analogies. While picturing a curved two-dimensional sheet helps build intuition, the four-dimensional curvature includes time, leading to effects such as gravitational time dilation, where time runs slower in stronger gravitational fields, and gravitational lensing, where the path of light bends around massive objects due to spacetime curvature. Moreover, Einstein's theory provides the mathematical framework necessary to describe phenomena such as black holes and gravitational waves, ripples in spacetime itself, recently observed by advanced detectors, confirming Einstein's predictions nearly a century later. In the context of cosmic expansion, spacetime's dynamic nature implies that it is not merely galaxies moving apart in a passive space, but space itself stretching over time. The galaxies are mostly at rest in their local neighborhood, yet the fabric between them expands, increasing the distances as a function of cosmic time. This phenomenon, sometimes called the metric expansion of space, is a direct consequence of general relativity applied on the largest scales. Cosmologists use Einstein's equations to develop models of the universe that incorporate its contents: ordinary matter, radiation, dark matter, and dark energy, and describe its shape, evolution, and ultimate fate. Quantities like the curvature of space, the rate of expansion, quantified by the Hubble parameter, and the energy densities of cosmic components are all interconnected through relativistic equations. The Big Bang model, dark energy's influence on accelerating expansion, and the cosmic microwave background's features are all understood within this relativistic framework. Understanding the fabric of spacetime also helps address perplexing questions about the nature of time, causality, and the horizon problem. The reason we observe remarkable uniformity in regions that seemingly could never have exchanged information due to finite light speed. The theory of cosmic inflation, an extension of relativistic cosmology, proposes a rapid early expansion that solves some of these puzzles. In essence, Einstein's conception of spacetime dismantles the intuitive but limiting notion of space as an empty container waiting to be filled. Instead, space and time are dynamic entities infused with geometry and intimately linked to the matter and energy they contain. This insight is crucial to understanding cosmic expansion, where it is the very stage of existence that is expanding, not just the objects within. As we move forward, this framework of curved dynamic spacetime will serve as the foundation upon which we explore related concepts like dimensions beyond the familiar, 3 of space and 1 of time, the challenges of visualizing expansion, and the deeper mathematical models that describe the universe's geometry and destiny. By embracing Einstein's revolutionary view of the cosmos, we take a pivotal step toward unraveling the intricate dance of space, time, and expansion. A dance that continues to shape our universe and beckons us to ponder the profound question: if space-time itself is stretching, into what realm is it expanding? Having established the essential concept of space-time as a unified fabric that underlies our universe, we now venture into a deeper exploration of dimensions, the fundamental measures and ways we conceive of space, time, and even realms beyond our intuitive grasp. Understanding dimensions is crucial as it allows us to fathom how the universe expands, how space and time intertwine, and what implications this may have on the very nature of reality itself. In daily life, we naturally perceive the world in 3 spatial dimensions: length, width, and height. These 3 dimensions form the physical space in which objects exist and events occur. We can move forward and backward, left and right, up and down. These dimensions give structure to the physical universe and provide the coordinates necessary to specify locations. Beyond our spatial experience lies the 4th dimension: time. Unlike the 3 dimensions of space, time is not a direction we can visit at will. Instead, time flows inexorably forward, ordering events and changes. While our senses perceive time as linear and unidirectional, physics reveals that time is as integral to the universe's fabric as space itself. Together, space and time form the 4-dimensional continuum called spacetime. This 4-dimensional perspective was a hallmark of Einstein's theory of relativity, which shows that the separation between space and time is not absolute, but dependent on the observer's motion. Events that appear simultaneous to one observer may be sequential to another. Time, along with space, bends and stretches under the influence of mass and energy, leading to phenomena like time dilation near massive bodies or at relativistic speeds. But dimensions need not stop at 4. Theoretical physics, particularly in fields such as string theory and quantum gravity, posits the existence of additional spatial dimensions beyond those we experience. These higher dimensions are typically compactified or curled up at scales so tiny that they elude direct detection. Their presence, however, may be crucial for reconciling quantum mechanics and general relativity into a unified framework. Imagine these extra dimensions as hidden corridors or layers of reality folded within the fabric of spacetime, affecting fundamental forces and particles in subtle ways. In M theory, a leading candidate for a theory of everything, as many as 11 dimensions are proposed, expanding both the mathematical beauty and complexity of our universe. The mathematical exploration of dimensions also informs cosmological models. For example, the shape and geometry of the universe depend on the curvature of these dimensions. Whether the cosmos is flat, open, or closed touches upon how dimensions curve collectively, influencing expansion, fate, and the universe's topology. To build intuitive understanding, one might consider lower dimensional analogies. A 2-dimensional creature confined to a plane would have no concept of up or down beyond their plane. Similarly, our three-dimensional perspectives could be limited regarding higher dimensions. Such analogies underscore the humbling reality that our awareness is rooted in a limited subset of the universe's possible dimensional structures. Time itself can be thought of as a dimension that, while distinct from spatial dimensions, still behaves in ways entwined with space. The expansion of the universe is not just a stretching of lengths, but involves the dynamic evolution of spacetime as a whole, where time unfolds in concert with spatial growth. Expanding our view beyond familiar dimensions extends the horizon of what is conceivable. It opens questions. Could there be universes with more dimensions? How might these unseen dimensions influence the physics we observe? How do these dimensional considerations affect the way space expands? Might expansion involve more than just the dimensions accessible to our senses? These profound questions are not mere flights of fancy, but active areas of scientific research. Instruments such as particle accelerators, gravitational wave detectors, and cosmological observatories provide data that may one day hint at these hidden realms. Meanwhile, advanced mathematics continues to push the boundaries of dimensional theory, seeking deeper unity in the laws of nature. As we absorb the significance of space, time, and higher dimensions, we are reminded that our universe is vast not only in its spatial extent, but in the complexity of its underlying structure. This expanded dimensional understanding sets the scene for grappling with the nature of cosmic expansion itself and how we attempt to visualize or depict this stretching of spacetime. In the following chapter, we will explore such visualizations, including the famous balloon analogy, which serves as a helpful but limited tool to conceptualize expansion. While analogies assist in grasping abstract ideas, they also expose the challenges inherent in representing dimensions and expansion within the bounds of human experience. Thus, embracing the multidimensional fabric of reality enriches our journey, inviting us to see the universe not merely as an empty void dotted with stars, but as a dynamic, dimensional tapestry endlessly expanding beyond the limits of perception. To begin visualizing the concept of the universe's expansion, one of the most influential and enduring analogies is the balloon analogy. This simple yet powerful metaphor has played a significant role in education and popular science, providing a tangible way to comprehend an otherwise abstract and counterintuitive phenomenon. However, while the balloon analogy offers an accessible entry point into understanding cosmic expansion, it also has its limitations and can lead to misconceptions if taken too literally. Exploring both its strengths and drawbacks will help us appreciate the nuanced reality of how the universe expands. Imagine a balloon with small dots marked on its surface, each dot representing a galaxy. As you slowly inflate the balloon, the surface stretches, and each dot moves away from every other dot. The farther apart two dots are, the faster they move away from each other. This mirrors the observation in cosmology that galaxies appear to be receding from one another, with more distant galaxies receding faster, a cornerstone of Hubble's law and evidence of cosmic expansion. This analogy brilliantly illustrates several important features. Firstly, it conveys the idea that expansion is not about galaxies moving through space away from some central point, but about space itself stretching, causing the distances between galaxies to increase. The balloon's surface itself expands uniformly, and there is no center on the surface from which all points recede. Similarly, in our universe, there is no preferred center of expansion. Every observer, regardless of location, would perceive other galaxies as moving away. Secondly, the analogy helps visualize the concept of metric expansion, the increasing scale of the space between objects rather than objects moving within a static space. It's not galaxies flying outward into emptiness, but rather the fabric of space itself growing, carrying the galaxies with it. Just as the dots are carried apart by the balloon's surface expanding. Despite these strengths, the balloon analogy has limitations rooted in the physical differences between the model and the actual universe. The balloon's surface is two-dimensional, whereas our universe possesses 3 spatial dimensions plus time. Visualizing a higher dimensional expansion within our 3-dimensional experience is inherently challenging, and the analogy's dimensional restriction can inadvertently constrain understanding. Furthermore, the balloon expands into a surrounding 3-dimensional space, the air outside the balloon, implying there is something outside the balloon that it can expand into. In contrast, the universe does not expand into a pre-existing space or void. Space itself is what grows. There is no external space outside our universe in the way the balloon expands into the room around it. This difference is subtle but essential because it addresses the very question posed at the heart of our exploration. What is the universe expanding into? Additionally, the balloon analogy represents points on the balloon's surface as galaxies, but it often suggests that galaxies are merely points on a surface rather than occupying a volume. Our universe is a 3-dimensional volume expanding in 3 dimensions, not a 2-dimensional surface expanding in a 3rd dimension. Another common misinterpretation arises when considering the center of expansion. In the balloon analogy, while the surface has no center for the dots on it, the balloon itself has a center in 3-dimensional space around which it inflates. This can mislead people into searching for a center point within our universe's higher dimensional embedding space, a concept that modern cosmology does not support. The universe has no center in ordinary 3-dimensional space. Rather, expansion is uniform throughout. Moreover, while the analogy captures uniform expansion well, it does not adequately represent how gravity and local forces affect the motion of galaxies, particularly galaxies in clusters that do not participate in cosmic expansion because they are gravitationally bound. In reality, cosmic expansion is a large-scale phenomenon observable over enormous distances, not affecting small, gravitationally cohesive systems. Finally, the balloon analogy does not convey the dynamics of expansion, that the rate of expansion has changed over time, including periods of acceleration due to dark energy and deceleration influenced by matter density. The analogy represents steady, uniform inflation, which simplifies but does not capture these temporal complexities. Despite these limitations, the balloon analogy remains a valuable pedagogical tool. It helps us confront the unfamiliar by relating cosmic expansion to everyday experiences, encouraging us to visualize growth without a center or edge in the familiar setting of a 2-dimensional surface. By recognizing its limitations, we avoid misunderstandings and prepare ourselves to delve into more sophisticated and abstract mathematical descriptions of the universe's expansion. As we continue, our next step is to explore common misconceptions surrounding cosmic expansion, how the universe expands, what that expansion does and does not mean, and how careful interpretation is necessary to avoid fallacies. From there, we will consider the nature of the universe's edge, boundaries, and the intriguing and deeply challenging question: does the universe have a boundary? And if so, what lies beyond? This journey through visualizing expansion underscores a core theme. Our cosmos is often stranger and more profound than any simple image or analogy can fully capture. Yet these metaphors remain indispensable in bridging the gap between the abstract and the comprehensible, enabling our minds to stretch towards the infinite. As we continue to explore the cosmos and its mysterious expansion, it is crucial to clarify what we mean when we say the universe is expanding. This seemingly straightforward phrase can be misleading, and common misconceptions abound. Misunderstandings often arise because cosmic expansion challenges everyday experiences and our intuitive grasp of space and motion. To truly appreciate the nature of the universe's growth, it's important to unravel these misconceptions and reveal the precise meaning behind expansion in a cosmological context. One widespread misconception is to imagine that galaxies, and the universe itself, are expanding like a conventional explosion from a particular point in space, with matter flying outward into empty space. This image suggests a central origin and an edge beyond which there is emptiness. However, the actuality is quite different. The universe has no center or edge in the conventional sense. Instead, space itself is stretching everywhere, carrying galaxies with it. This means every observer, no matter where located, sees other galaxies moving away, often described metaphorically as dots on an inflating balloon's surface, with no distinct center on that surface. Another misunderstanding is to think that galaxies themselves are expanding. In fact, most galaxies are gravitationally bound systems whose internal structures resist the cosmic expansion. The atoms, stars, planets, and even clusters of galaxies remain relatively intact. Cosmic expansion primarily affects the large-scale structure of space between these gravitationally bound regions, meaning the vast voids between galaxies and clusters grow larger over time. People may also confuse the Doppler effect caused by galaxies moving through space with redshift resulting from the expansion of space itself. The Doppler effect involves objects moving relative to a fixed backdrop, like a car passing by and its horn's pitch altering. In cosmology, redshift is mainly due to the stretching of space, increasing the wavelength of light traveling through it. This cosmological redshift differs fundamentally from motion through space and stems from the expansion of the metric that defines distances. Relatedly, it is often thought that galaxies recede from us at speeds limited by the speed of light, yet observations indicate that distant galaxies exhibit recession velocities exceeding light speed due to the expansion of space between us. This does not violate Einstein's relativity, because the galaxies aren't moving through space faster than light. Instead, the space between expands, increasing their separation at effective superluminal rates. This nuance is subtle but vital to avoid confusion. Another prevalent confusion concerns the idea of the universe expanding into something. Many visualize the universe as a balloon inflating into pre-existing empty space, seeking to understand what lies outside. However, current cosmological understanding suggests that expansion doesn't occur into an external space. Rather, space itself is being created and stretched. The universe doesn't require an embedding space for its expansion. It is self-contained as a four-dimensional spacetime entity. The concept of outside does not align naturally with our universe's geometry as described by modern physics. Furthermore, people often assume that the expansion of the universe implies an increase in overall density, or that matter is being created continuously. In reality, as space expands, the average density of matter decreases because the same amount of matter is spread over an increasing volume. This dilution is a natural consequence of expansion without implying any loss or gain of matter. There is also a tendency to think of time when cosmic expansion occurs as a universal clock ticking identically everywhere. However, due to relativity, time is relative and can run differently depending on gravitational fields and motion. Cosmic expansion is framed within the fabric of spacetime, where both space and time dimensions evolve together. Additionally, while cosmic expansion suggests distances grow, objects bound by forces, like atoms or solar systems, are governed by physics that negate expansion effects locally. Thus, the same rules that govern cosmic expansion do not apply to small scales due to gravitational, electromagnetic, and nuclear forces. By dispelling these misconceptions, we arrive at a richer, more accurate picture. The universe's expansion is a large-scale stretching of the metric that defines distances in space and time without a center or edge, not an explosion into an external void, and not a process that expands objects themselves. It is a profound, dynamical deformation of spacetime woven directly into the fabric of our cosmos. This nuanced understanding equips us to ponder deeper questions. If the universe has no edge or center, what then does it mean to have an edge, and what lies beyond? Is there an outside at all? These very questions lead us to the following exploration of the universe's boundary, or lack thereof, and the intriguing concept of what, if anything, exists beyond the cosmic horizon. Embracing this refined perspective on expansion prepares us to engage more thoughtfully with the profound challenges of cosmology, and invites us to continue the journey with open minds, ready for the marvels and mysteries that the universe holds. The vastness of the universe continues to ignite the human imagination, beckoning us to ponder one of the most profound and enduring questions. Does the universe have an edge or a boundary? We are accustomed to encountering boundaries in our daily lives: a fence enclosing a field, a coastline marking the end of land, or horizons limiting our view. But when it comes to the cosmos, the question of an edge transcends simple analogy and ventures into the realm of complex cosmological understanding. To begin unraveling the question of a universe's boundary, it is crucial to distinguish between what we can observe and what might exist beyond our observational reach. The observable universe is a sphere approximately 93 billion light-years in diameter, defined by the furthest distance light has traveled to reach us since the cosmos emerged from the Big Bang. Beyond this sphere lies a realm currently inaccessible to us because light or any signals from there have not had time to arrive. This observational boundary, often called the cosmic horizon, is not a physical edge, but a limit of our knowledge and visibility. But does this cosmic horizon correspond to an actual boundary in space? The prevailing consensus in modern cosmology is that it does not. The observable universe is not a cosmic island bounded by an edge, but rather a limited portion of a possibly much larger, or perhaps infinite, universe. The horizon moves outward as time passes, continually revealing new parts of the cosmos to us, marking the ever-expanding sphere of what we can observe. Scientific models, grounded in Einstein's theory of general relativity, describe the universe's geometry and topology, the shape and connectedness of space. These models allow for several possibilities about the universe's overall structure. It could be closed, like the three-dimensional analog of a sphere, flat or open, with negative curvature. If the universe is closed and finite, it would have no edge in the conventional sense. Much like the two-dimensional surface of a sphere has no edges yet is finite. The three-dimensional universe could similarly be finite yet unbounded, curving back on itself so that traveling far enough in one direction might eventually bring you back to your starting point. Alternatively, if the universe is infinite and flat or open, then it extends endlessly in all directions without any edge or boundary at all. Current observations, especially those analyzing the cosmic microwave background radiation, indicate that the universe is remarkably flat on large scales. But whether it's infinite or simply very large remains an open question. The concept of boundary carries with it another challenging notion. What would lie beyond such a boundary? If the universe encompasses all of space and time, the idea of an external outside is problematic. Unlike a terrestrial boundary, which separates inside from outside, the universe may not be embedded in anything larger. It doesn't expand into a pre-existing space. Rather, space itself is what expands. This defies everyday intuition, making it difficult to imagine what an edge of the universe would be, or what could lie beyond. Speculative theories have proposed scenarios such as multiverses, collections of possibly disconnected or diverse universes. But even in these frameworks, each universe might be self-contained, without a well-defined edge from the inside, leaving the concept of boundary as a subtle matter of topology rather than a physical barrier. Philosophically, the question of the universe's boundary touches on broader debates about the nature of infinity, existence, and the limitations of human comprehension. The universe as boundless challenges us to stretch our minds beyond finite experiences, grappling with concepts that resist direct observation or physical analogy. In conclusion, current understanding suggests the universe does not have an edge or boundary in the everyday sense. Instead, it either extends infinitely or is finite but unbounded, with no edges marking the end of space. Our observable universe remains a limited window onto this vast expanse, bounded only by what light has reached us so far. This realization naturally leads us to our next contemplation. What might it mean to speak of what lies outside the universe? If there is no boundary, what exactly would beyond the universe entail? This perplexing question invites us to explore the nature of outside the universe itself, a topic both deeply scientific and profoundly philosophical, as we continue our quest to grasp the cosmos in all its enigmatic breadth. The question of what lies outside the universe is as captivating as it is elusive, stretching the limits of human imagination and scientific inquiry. In everyday life, the concept of outside is straightforward, a space beyond the boundaries of a room, a country, or a planet. But when applied to the universe, the notion becomes profoundly complex and, in many respects, defies conventional understanding. To grasp why, we must start by revisiting what the universe actually encompasses. The universe is commonly defined as all of space and time, everything that exists physically, including matter, energy, and the very fabric of spacetime itself. It is the totality of all that is, or at least all that can be observed and measured. In this sense, outside the universe would necessarily be outside all physical existence, a concept so abstract that it challenges the very foundation of what we consider meaningful existence. One way to approach this is through analogy, mindful of its limitations. Consider the two-dimensional surface of a sphere, like the surface of the Earth. To a creature inhabiting only this surface, there is no concept of outside the sphere. Their world is curved but finite and unbounded. The third spatial dimension, which provides the notion of outside, is beyond their perception. Similarly, our three-dimensional universe might be analogous, a three-dimensional manifold without any higher dimensional outside accessible or even existent to our reality. Modern cosmology, built on Einstein's general relativity, models the universe as a four-dimensional spacetime that often is described as either finite and unbounded or infinite. But crucially, the universe is self-contained. It doesn't require an external frame or embedding space to exist or expand. This intrinsic property means that asking, "What is outside the universe?" is not merely to ask a difficult scientific question. It's to ask a question that might be fundamentally meaningless within our current physical framework. Yet, physicists are no strangers to exploring beyond conventional limits. several theoretical models contemplate the existence of spaces or domains beyond our own universe, often in the context of multiverse theories or higher dimensional spaces posited by string theory and related fields. These suggest that our universe might be one brain among many in a higher dimensional space, or that countless universes with differing physical laws may exist in a grand cosmic ensemble. In these speculative frameworks, outside the universe could correspond to this higher dimensional bulk space or the milieu in which multiple universes coexist. However, such spaces are theoretical constructs without empirical evidence at present, and their properties, and even their very existence, remain under vigorous debate in the scientific community. Furthermore, the concept of outside depends heavily on how we define the boundaries of what we call a universe. If an entire space-time continuum is the universe, then there may be no extension beyond it to speak of. But if universes are defined more narrowly through observable domains or distinct physical constants, then an outside might exist, albeit inaccessible to us. Philosophically, this inquiry touches on questions about the limits of knowledge, the nature of existence, and the human impulse to seek borders and origins. When science currently encounters such frontiers, it often signals the need for new conceptual frameworks or deeper mathematical languages to meaningfully describe the cosmos. In summary, the notion of outside the universe defies the confines of everyday intuition and current physical laws. Within our best scientific understanding, the universe is either everything that exists or part of a more complex multiversal structure yet to be fully comprehended. The question remains open, inviting ongoing curiosity, rigorous investigation, and perhaps new paradigms. As we proceed, this profound mystery encourages us to delve into concepts that extend beyond observable reality. Higher dimensions, theories of the multiverse, and the mathematical models that attempt to bridge the known with the conceivable. These explorations offer hope that, although outside the universe remains enigmatic, human imagination and inquiry continue to push the boundaries of understanding toward the infinite. As we journey deeper into understanding the cosmos and the profound mysteries surrounding its expansion, we inevitably encounter concepts that challenge not only our physical intuition, but also the very nature of reality itself. Higher dimensions, and the multiverse. These ideas, once purely speculative, have become integral parts of cutting-edge theoretical physics, offering rich yet complex frameworks that seek to explain phenomena beyond the reach of established models. The notion of higher dimensions extends the familiar 3 spatial dimensions and 1 temporal dimension into realms that are difficult to visualize, yet mathematically compelling. Theories such as string theory and its extension, M theory, suggest that our universe might consist of up to 11 dimensions, the extra 7 of which are compactified, curled up so tightly that they evade direct detection at macroscopic scales. These additional dimensions provide the mathematical scaffolding necessary to unify the fundamental forces of nature, including gravity and quantum mechanics, which have stubbornly resisted integration within traditional frameworks. Within this multidimensional landscape, our perceivable universe exists as a 3-dimensional brain embedded in a higher dimensional bulk. This brain world scenario posits that while electromagnetic forces and particles are confined to our brain, gravity may permeate the extra dimensions, potentially explaining why it appears weaker compared to other fundamental forces. This perspective radically alters how we envision the structure of reality, suggesting that our universe is but a slice of a richer, higher dimensional cosmos. Closely allied with these ideas is the concept of the multiverse, an astounding hypothesis that there exist not just one, but many, perhaps infinitely many, universes. The multiverse emerges from various theoretical avenues: the landscape of string theory, with its vast vacuous solutions, the eternally inflating cosmos producing pocket universes with varying physical constants, and interpretations of quantum mechanics, such as the many worlds interpretation. In cosmological inflation theory, for instance, the universe undergoes rapid exponential expansion shortly after the Big Bang, and this inflation may never cease in regions beyond our cosmic horizon. Such models naturally give rise to a fractal-like multiverse, where countless bubble universes emerge, each with its own laws of physics, particle contents, and even dimensional configurations. Our observable universe would be just one such bubble within an incomprehensibly vast multiversal expanse. These concepts offer tantalizing explanations for otherwise perplexing puzzles. Why do the constants of nature have the precise values necessary for life? The multiverse suggests that while most universes may be inhospitable, we find ourselves in a rare one suited for observers, a form of the anthropic principle. Moreover, higher dimensions provide mechanisms to reconcile gravity with quantum forces, potentially paving the way to a theory of everything. Yet, these concepts are ripe with challenges. Their inherently speculative nature and the current impossibility of direct empirical testing place them at the frontier between physics and philosophy. Scientific rigor demands that hypotheses be testable and falsifiable, and so researchers actively seek indirect pathways, such as signatures in the cosmic microwave background radiation, gravitational waves, or particle physics experiments, to gather evidence supporting or refuting multiverse and higher dimensional models. Mathematically, these theories rely on sophisticated constructs such as Calabi-Yau manifolds for compactified dimensions and complicated vacuum landscapes with an astronomical number of solutions. The sheer complexity fuels debates about scientific methodology and the limits of human understanding. In contemplating higher dimensions and the multiverse, we glimpse a universe, or better, an ensemble of universes, that is vastly richer and stranger than everyday experience suggests. These frameworks push us beyond the confines of familiar space and time, inviting profound questions about reality's fabric and our place within it. As we prepare to explore more precise mathematical descriptions of the universe's geometry, we carry with us the awareness that our cosmos might be but a facet of a grander, multidimensional, and potentially infinite multiverse. This realization not only broadens our scientific horizons, but also deepens the philosophical and existential musings that have accompanied humanity's quest to grasp the cosmos. In the upcoming section, we will delve into the mathematical models that describe the universe's shape, whether flat, open, or closed, and how these geometric frameworks relate intimately to concepts of expansion, boundaries, and the very architecture of reality itself. Understanding the geometry of the universe is fundamental to grasping its overall shape, structure, and destiny, especially in the context of its expansion. Modern cosmology uses mathematical models grounded in Einstein's general relativity to explore whether the universe is flat, open, or closed. These geometric classifications describe the curvature of space at large scales and have profound implications for the universe's fate and the nature of the expansion itself. To illustrate these ideas, it helps to return to familiar lower-dimensional analogies. Imagine the two-dimensional surface of various shapes: a sphere, a flat plane, and a saddle-shaped surface. Each represents a different type of curvature: positive, zero, and negative, respectively. Although these are two-dimensional, they serve as instructive analogies for comprehending three-dimensional spatial curvature. A closed universe corresponds to positive curvature, analogous to the surface of a sphere. It is finite, yet unbounded. If you travel far enough in one direction, you might return to your starting point. This kind of geometry implies a universe that is curved back upon itself, with space bending so that the rules of Euclidean geometry no longer hold exactly. For example, the angles of a triangle on such a surface add up to more than 180 degrees. An open universe exhibits negative curvature, similar to a saddle's surface. It is infinite and unbounded, with space diverging in all directions. Here, Euclidean geometry is altered so triangle angles sum to less than 180 degrees, and parallel lines eventually diverge. In this scenario, the universe will continue expanding forever, with curvature influencing how galaxies cluster and light travels across cosmic distances. Finally, a flat universe has zero curvature, conforming closely to the Euclidean geometry many of us learn in school. Parallel lines remain parallel. Angles in triangles add up exactly to 180 degrees, and space extends infinitely without closing back on itself. This model also predicts that the universe will expand forever, but at a rate sensitive to its energy content. Cosmologists parameterize curvature through the density parameter, often denoted omega-O, which compares the actual density of matter and energy in the universe to a critical density required for flatness. If H=1, the universe is closed. If O1, it is open, and if O=1, it is flat. Matter, radiation, dark matter, and especially dark energy all contribute to the overall energy density affecting this parameter. Observations over the past few decades, including precise measurements of the cosmic microwave background radiation by missions such as WMAP and Planck, strongly indicate that the universe is extremely close to flat. The measurements of temperature fluctuations across the sky, combined with large-scale structure surveys and supernova data, converge toward O=1 unity within small uncertainties. Yet, even if flat, the universe can be infinite or extremely large but finite if topologically complex. Additionally, the presence of dark energy, responsible for accelerating expansion, modifies the geometry's dynamics. Mathematically, the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric provides the framework to describe these geometries in expanding universes, parameterizing spacetime with scale factors that evolve over time. Solutions to Einstein's field equations describe how the scale factor changes and how expansion proceeds under different curvature and energy density conditions. The shape impacts the universe's ultimate fate. A closed universe might eventually halt expansion and recollapse in a big crunch. An open or flat universe will expand forever, with dark energy potentially causing accelerated expansion that leads to a big freeze, or heat death. These fates connect geometry, energy content, and expansion in a cosmic dance governed by physical laws. Understanding the universe's geometry also helps address observational phenomena like gravitational lensing, the propagation of light across vast distances, and patterns in the cosmic microwave background. It informs where galaxies end up and how structures evolve. The elegance of these mathematical models lies not only in their descriptive power, but in their ability to unify seemingly disparate observations into a coherent picture of cosmic evolution. They invite us to view the universe not merely as a collection of objects, but as a geometric entity whose shape and fabric define the possibilities of existence and expansion. As we move forward, this insight into the universe's geometry will provide critical context for interpreting cosmic background radiation, understanding the concept of metric expansion, and exploring how dark energy affects the acceleration of that expansion. A journey weaving together mathematics, observation, and philosophical reflection as we continue to unravel what the universe is expanding into. The cosmic microwave background radiation, often simply called the CMB, stands as one of the most profound discoveries in cosmology, providing a unique window into the universe's infancy and offering critical evidence supporting the Big Bang model. To understand its significance, we must embark on a journey deep back in time, nearly 13.8 billion years ago, to moments shortly after the universe's birth. In the earliest epochs, the universe was a searingly hot, dense plasma of particles, protons, electrons, photons, and other fundamental particles, so energetic that photons were continually scattered by free electrons in a fog-like state. This primordial plasma was opaque to light. Photons could not travel freely but were constantly absorbed and re-emitted, analogous to dense fog scattering sunlight. As the universe expanded and cooled, it reached a pivotal point about 380,000 years after the Big Bang, known as recombination. During recombination, temperatures dropped sufficiently for protons and electrons to combine into neutral hydrogen atoms. This allowed photons to decouple from matter, starting to travel freely through space for the first time. These photons constitute the cosmic microwave background radiation, a relic glow permeating all of space. Today, due to the universe's continuous expansion stretching the wavelength of these primordial photons, the CMB manifests as faint microwaves with a blackbody temperature of approximately 2.7 Kelvin, just above absolute zero. This cooling and redshifting of the original high-energy radiation embody the universe's expansion in a tangible form. The CMB was serendipitously discovered in 1965 by Arno Penzias and Robert Wilson, whose sensitive antenna detected persistent microwave noise that turned out to be this ancient cosmic signal. This observation was landmark evidence confirming the Big Bang theory while ruling out alternative steady-state models that could not account for such residual radiation. Detailed measurements of the CMB, especially by satellites like COBE, WMAP, and Planck, have revealed exquisitely subtle fluctuations in temperature and polarization across the sky. These anisotropies encode vast amounts of information about the early universe's contents, geometry, and evolution. Tiny density fluctuations present in the primordial plasma eventually served as the seeds for cosmic structure, galaxies, clusters, and vast cosmic webs. The CMB observations have been instrumental in determining fundamental cosmological parameters, such as the universe's curvature, supporting a flat geometry, the proportions of ordinary matter, and dark energy, and the Hubble constant that quantifies expansion rate. In essence, the CMB acts as a cosmic blueprint, enabling cosmologists to reconstruct the universe's timeline and its large-scale properties. Moreover, the CMB empowers us to look back in time with unprecedented precision, offering a snapshot of the universe at a mere fraction of its present age. It bridges the gap between theoretical predictions and empirical reality, anchoring our scientific models. Further studies have probed secondary effects on the CMB, such as gravitational lensing by massive structures and the Sunyaev-Zeldovich effect, deepening our insights into late-time cosmic evolution. The cosmic background radiation thus epitomizes the concept of, when astronomers speak of the universe expanding, they are referring to a phenomenon much deeper and more nuanced than objects simply moving apart through a pre-existing space. Instead, the concept at the heart of cosmic expansion is the stretching of space itself, a notion known as metric expansion. To truly appreciate what it means for space to grow, we must explore what a metric is, how it defines distances, and why the universe's fabric evolves in a way that leads to increasing separation between distant galaxies. In geometry and physics, a metric is a mathematical tool that specifies how distances are measured between points in space. It goes beyond simply assigning coordinates. It encodes the rules for calculating lengths and angles, taking into account the curvature, shape, and dimensionality of the space itself. In everyday life, the Euclidean metric applies, where distance is determined by the familiar Pythagorean rule. But on cosmic scales, the rules can be far more intricate, reflecting the dynamic and curved nature of spacetime described by Einstein's general relativity. Metric expansion is the increase over time of this distance measure on large scales, meaning that the very scale used to define lengths between galaxies changes. Imagine drawing dots on a rubber sheet and slowly stretching it. The dots move apart not because they themselves traveled, but because the sheet, the space they rest on, grew larger. Similarly, galaxies are not flying through space in any classical sense, but are carried away by the expansion of the metric defining the space between them. This expansion is uniform and isotropic, meaning it occurs the same way everywhere and in every direction, ensuring that no point is uniquely central or privileged. Every observer, regardless of location, perceives nearby galaxies moving away, with distant galaxies receding faster, consistent with Hubble's law. This observation arises naturally from metric expansion without requiring the universe to have a center or edge. Mathematically, cosmologists describe this behavior using the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric, a solution to Einstein's field equations under the assumptions of homogeneity and isotropy. The FLRW metric introduces a scale factor, a function of cosmic time that encodes how distances between fixed points evolve. When the scale factor increases, we interpret this as the expansion of space itself. Importantly, metric expansion applies predominantly at cosmological scales. On smaller scales, objects bound by forces such as atoms, planets, stars, and even galaxies do not expand. Their internal interactions counter the stretching of space, maintaining their size and structure. Thus, households, solar systems, or galaxies do not grow simply because space grows. Expansion is most apparent in the vast, mostly empty intergalactic voids where gravitational binding is weak. Moreover, light traveling through expanding space is stretched, causing the observed cosmological redshift. Photons emitted billions of years ago reach us with longer wavelengths because the metric of space stretched during their journey. This redshift directly traces the expansion history encoded in the scale factor. Crucially, metric expansion differs fundamentally from motion in space described by special relativity. No galaxy moves locally faster than the speed of light. Rather, the intervening space between galaxies stretches, allowing effective recession velocities exceeding light speed without violating physical laws. At an intuitive level, metric expansion challenges our everyday experiences, which are rooted in static, flat space, and time. It requires embracing a dynamic geometry where space itself grows, influencing how distances and horizons evolve over cosmic time. This dynamic underlies phenomena like the cosmic horizon, the limit beyond which light can no longer reach us due to rapid expansion. Understanding metric expansion sets the stage for deeper insights into cosmic acceleration, the role of dark energy, and the universe's ultimate fate. It frames expansion not as an explosion into pre-existing emptiness, but as an intrinsic stretching of the universe's very fabric, an unfolding that continues to shape the cosmos. As we proceed, this foundation will enable us to navigate the complex terrain of dark energy and the accelerated expansion it drives, as well as engage with philosophical and scientific questions about the nature of cosmic growth and what, if anything, the universe might be expanding into. In the late 1990s, a remarkable and unexpected discovery forever transformed our understanding of the cosmos. The universe's expansion isn't slowing down, as once believed, but rather accelerating. This acceleration is attributed to a mysterious phenomenon known as dark energy. which today is understood as constituting roughly 68% of the total energy content of the universe. To comprehend dark energy and its role in cosmic expansion is to grasp one of the deepest enigmas in physics and cosmology. For much of the 20th century, scientists anticipated that gravity's attractive pull would gradually decelerate the universe's expansion, much like a ball thrown upward eventually slows under Earth's gravity. The critical question was whether this deceleration would halt and reverse, leading to a big crunch, or whether expansion would continue eternally, slowing asymptotically. However, observations of distant-type Ia supernovae in the late 1990s shattered these assumptions. Two independent research teams found that these supernovae appeared dimmer than expected, indicating they were farther away than predicted by decelerating models. This discovery pointed to a startling conclusion. The expansion rate of the universe is increasing with time. To explain this cosmic acceleration, physicists introduced the concept of dark energy, a pervasive, enigmatic form of energy with repulsive gravitational effects. Unlike normal matter and energy, which attract through gravity, dark energy appears to produce a pressure that drives space apart, accelerating expansion. Dark energy's precise nature remains elusive. The simplest explanation is Einstein's cosmological constant, introduced originally as a fudge factor to allow a static universe, but now reinterpreted as vacuum energy, the energy inherent in empty space itself. This vacuum energy has a constant density even as space expands, exerting a negative pressure that tends to accelerate the universe's growth. Alternate theories propose dynamic forms of dark energy, such as quintessence, involving scalar fields that evolve over time. Other speculative ideas include modifications to general relativity on cosmic scales or exotic phenomena like phantom energy, which could lead to dramatic futures like the Big Rip, where space tears itself apart. The presence of dark energy drastically alters the universe's fate. Instead of slowing and recollapsing, or coasting along endlessly, the acceleration suggests that galaxies outside our local group will recede increasingly faster, eventually crossing horizons beyond which we can never observe or reach them. Matter becomes diluted, star formation dwindles, and over unimaginably long timescales, the cosmos approaches a cold, dark, and diffuse state known as the heat death. Despite its dominant role, dark energy remains detected only indirectly through its gravitational effects on cosmic expansion and structure formation. Precise observations of the cosmic microwave background, galaxy distributions, gravitational lensing, and supernovae distances help constrain models and parameters. Projects like the Dark Energy Survey, the Euclid Satellite, and the upcoming Nancy Grace Roman Space Telescope aim to unravel this cosmic mystery further. Philosophically, dark energy challenges our understanding at a fundamental level. What is this mysterious force permeating space? How does vacuum energy exist with such properties? Why does its density take the small but non-zero value observed? These questions are intimately tied to quantum field theory and gravity, inviting new physics at the intersection of microscopic theory and macroscopic cosmology. In the context of the universe's expansion, dark energy is the invisible hand accelerating space's growth, influencing the metric expansion described previously. Its discovery compels us to rethink cosmic evolution comprehensively, blending observation, theory, and speculation into a grand quest to understand the universe's destiny and the profound nature of the vacuum itself. As we proceed, exploring philosophical reflections on whether the universe can expand into nothing will lead us into deeper conceptual territory. We will also survey perspectives of leading physicists on these issues, grappling with how to represent and visualize such an intangible yet all-encompassing aspect of reality. In essence, dark energy stands as a reminder of how much remains unknown, even about the universe at the largest scales. It challenges our scientific ingenuity and philosophical insight, inviting us to continually expand the horizons of human knowledge alongside the expanding cosmos itself. The concept of the universe expanding into nothing invites one of the most profound philosophical and scientific questions about the nature of existence, space, and reality itself. At first glance, it might appear intuitive that for something to expand, it must do so into some surrounding space or void, some empty outside that receives the growing boundaries of the expanding object. Yet, modern cosmology challenges this intuition and compels us to reconsider what nothing means and whether the universe's expansion truly implies growth into anything external at all. Historically, the expansion of familiar objects, such as a balloon inflating or a gas filling a container, occurs within a pre-existing space. The balloon grows into the surrounding air. The smoke spreads into pre-existing atmosphere. These examples rest on the assumption of an embedding space that provides a backdrop or arena into which physical phenomena move or grow. Applying this analogy to the universe at large appears natural, but is deeply misleading. Scientific understanding grounded in the theory of general relativity reveals that space itself is dynamic, not a passive stage, but a participant in the cosmic story. Specifically, the metric describing distances in space stretches with time, and it is this metric expansion that defines the universe's growth. Importantly, this growth occurs everywhere and at once. There is no center from which space unfolds into emptiness, nor a boundary pushing outward toward an external realm. From a philosophical vantage point, the notion of nothing is not merely empty space, but the absence of anything, no matter energy, space, or time. To conceive the universe expanding into such absolute nothingness defies conventional understanding. In fact, it suggests a paradox. How can nothing serve as a container or arena for expansion if it lacks all properties, including space itself? The cosmological principle holds that the universe is homogeneous and isotropic on large scales, with no preferred directions or positions. This uniformity, coupled with the mathematics of spacetime, implies that our universe has no edge or boundary, and thus no external outside space for expansion to proceed into. Some philosophical interpretations propose that the universe might be self-contained, similar to the two-dimensional analogy of the surface of a sphere, which expands in a way that does not require an exterior embedding space. In this analogy, there is no outside to the sphere's surface, yet it is finite and unbounded. Extrapolating to higher dimensions, the universe can grow and expand without needing to occupy a larger pre-existing space. Quantum cosmology even suggests that space and time themselves emerged from a kind of quantum vacuum, or foam, with the fabric of spacetime being a dynamic entity shaped by underlying quantum processes. In these views, the classical notion of nothingness is replaced by a more subtle quantum substrate, blurring lines between something and nothing. However, from a metaphysical perspective, the idea that the universe expands into nothing raises troubling questions. It forces us to ask, are we dealing with limitations of human language and conceptions rather than physical reality? Is nothing a concept that has meaning outside of human thought? Can we apply spatial metaphors like inside and outside to something as all-encompassing as the universe itself? In alternative speculative frameworks, such as certain multiverse theories, there might be notions of outside an individual universe within a larger meta-reality. But these outer realms, if they exist, are beyond current empirical test and remain highly conjectural. Ultimately, the philosophical question of whether the universe can expand into nothing intertwines with deep issues about the origin of space and time, the limits of scientific explanation, and the nature of existence. Modern cosmology suggests that rather than expanding into an empty void, space itself is generated and stretched, defining its own boundaries internally without reference to an external arena. This realization nudges us toward a more subtle understanding of expansion, not as growth into an external place, but as evolution of the universe's own fabric. It highlights the profound challenge of reconciling human intuition about space with the strange and beautiful realities uncovered by science. As we move forward, considering what physicists say about these questions, how to visualize expansion accurately, and what scenarios the future holds for the universe's continued expansion, will further illuminate these mysteries. This inquiry sits at the fascinating boundary where cosmology meets philosophy, inviting us to reflect not only on the universe around us, but also on the nature of reality itself. As we stand on the cusp of some of the deepest questions about the universe, its expansion, boundaries, and what it might be expanding into, it helps enormously to hear the perspectives of the physicists who have devoted their lives to unraveling these cosmic mysteries. Their insights and debates not only reflect the complexity and subtlety of the subject matter, but also highlight the evolving nature of scientific understanding as new observations and theoretical frameworks emerge. One prevailing consensus among physicists is that the universe's expansion is best understood not as galaxies moving into an external space, but as the metric expansion of spacetime itself. This insight emanates from applying Einstein's general relativity to cosmology, leading to solutions like the Friedmann-Lemaitre-Robertson-Walker metric that describe a universe whose scale factor changes over time. Renowned cosmologists such as Stephen Hawking and Roger Penrose have articulated how this dynamic spacetime fabric challenges classical notions of space as a static stage. Yet beyond common ground lies robust debate. Some physicists emphasize the importance of clarifying misconceptions, noting that popular analogies, for example, the balloon analogy, while useful pedagogically, can inadvertently cause misunderstanding if taken literally. Physicists like Sean Carroll or Brian Greene advocate precise communication to convey that the universe lacks a conventional outside, and that expansion does not require space into which the universe grows. Extending beyond the classical framework, quantum gravity researchers explore ideas where spacetime itself emerges from more fundamental entities, potentially reshaping how expansion is framed. In loop quantum gravity, for example, spacetime has a discrete structure at the smallest scales, which may circumvent singularities like the Big Bang. Meanwhile, string theorists propose higher dimensional branes and multiverse scenarios that broaden the discussion about what constitutes the universe and its possible relationships to even grander structures. Within these debates is the unresolved challenge of dark energy and the acceleration of expansion. Scientists differ on whether dark energy is a true cosmological constant, a dynamical field like quintessence, or an indication that general relativity needs modification at cosmological scales. Leaders in the field, such as Nobel laureates Adam Rees, Saul Perlmutter, and theoretical physicists like Lisa Randall, engage actively in both observational campaigns and theoretical modeling to illuminate dark energy's nature. Several physicists also explore the philosophical and conceptual boundaries of cosmology. Penrose, for instance, has delved into the nature of time's arrow and how it links with the universe's expansion, while thinkers like Carlo Rovelli emphasize relational and emergent aspects of space and time rather than treating them as pre-existing containers. Debates exist on whether the universe is finite or infinite, whether it has a boundary or is unbounded, and how we can reconcile these ideas with the mathematical models and observational data. The intriguing question of what, if anything, the universe might be expanding into touches on the limitations of our current theories, where some physicists suggest the question may be ill-posed or point to the need for new physics beyond general relativity. Crucially, physicists stress the provisional nature of cosmological knowledge. As new telescopes, particle accelerators, gravitational wave detectors, and observational techniques advance, each discovery has the potential to refine or overturn existing paradigms. This openness defines science's strength and drives ongoing research into the deep mysteries governing our cosmos. In essence, expert insights reveal that while enormous progress has been made in describing and understanding cosmic expansion, fundamental questions remain tantalizingly open. These debates provoke deeper reflection on the nature of reality, the limits of human understanding, and the continuous quest to reconcile theory with observation. As we proceed, engaging with these expert perspectives enables us to appreciate not only what we know, but the frontiers where science boldly ventures into the unknown, shaping how future generations might understand the vast, expanding universe we inhabit. The universe's expansion is a concept so vast and abstract that representing it visually presents profound challenges, both for scientists trying to communicate complex ideas and for anyone seeking intuitive understanding. Unlike everyday objects whose growth or movement can be easily pictured within familiar three-dimensional space, the expansion of the universe involves the stretching of space itself, occurring in four-dimensional spacetime without a true center or external background. How then do we visualize or depict this expansion in ways that are both accurate and accessible? One of the most popular visual tools is the balloon analogy, where the surface of a balloon represents a two-dimensional universe dotted with galaxies, dots. Inflating the balloon increases the distances between dots, illustrating expansion without a center on the surface. While powerful, this analogy is limited. It uses a two-dimensional surface embedded in three-dimensional space to represent a three-dimensional universe expanding, and it might imply an outside into which the universe grows, a concept that our universe, as far as physics shows, does not have. Similarly, the raisin bread analogy depicts raisins embedded in dough that expands as the bread rises. The raisins, galaxies, move apart not by their own motion, but due to the expanding dough, space. Although this helps illustrate uniform expansion, it too risks oversimplifying and may lead to misconceptions about motion through space rather than expansion of space itself. Another challenge arises connecting mathematical models with visual intuition. Cosmologists work with highly abstract, multidimensional geometries described by metrics and tensors, which resist straightforward imaging. Dynamic expansion cannot be captured fully in static images or simple animations. Even the concept of distance varies locally due to curvature, relativistic effects, and evolving spacetime, complicating direct visualization. Beyond analogies, scientists use graphical representations like spacetime diagrams and scale factor plots to depict how distances between galaxies change over time. While less immediately intuitive, these provide more faithful representations aligned with relativistic physics. Animations showing galaxies receding in a grid, where grid cells stretch with time, help visualize metric expansion, but require careful explanation to avoid confusion. Visualizing horizons and limits of observation, regions beyond which light has not reached us, poses further difficulties. The cosmic horizon is dynamic, moving outward as time passes, and encoding it requires a temporal, four-dimensional awareness beyond common experience. Conceptual challenges intensify when trying to depict accelerating expansion due to dark energy, which changes expansion rates over time, or when considering higher dimensions and multiverse theories where the universe might be embedded in a larger space inaccessible to our senses. Despite these hurdles, visualization remains a vital bridge connecting our conceptual understanding with human cognition. It requires blending analogy with rigorous scientific depiction and honest communication about limitations. Educators and communicators strive to present models that elucidate rather than mislead, recognizing that all analogies are partial and must be supplemented with careful explanation. Emerging technologies like virtual reality and interactive simulations hold promise for deeper intuitions about expansion and cosmic structures, allowing users to immerse themselves within evolving models of the universe and appreciate scale, motion, and geometry from novel perspectives. In summary, representing the expansion of the universe challenges our innate spatial reasoning and stretches the limits of visual metaphor. Yet through thoughtful analogies, mathematical images, and new media, we gain valuable tools to imagine and engage with the extraordinary reality of cosmic expansion. A universe growing not into some external void, but within the very fabric of space-time itself. With this awareness, we are better equipped to approach the next topics, contemplating the future scenarios of expansion, from eternal growth to ultimate fate, and reflecting on the human endeavor to grasp a universe seemingly beyond measure or boundary. As we look toward the distant future, the trajectory of the universe's expansion raises profound questions about its ultimate fate. What will happen if the universe continues to expand indefinitely? Could it slow down, reverse, or change in unforeseen ways? Scientists have developed several key scenarios grounded in contemporary cosmological models and observational data, painting diverse possibilities that captivate both our imagination and scientific inquiry. One scenario is that the journey to comprehend the universe's vast expansion is not just a scientific endeavor, but a profound cultural and educational challenge. How the public perceives, understands, and internalizes concepts like the expanding cosmos, dark energy, and cosmic origins shapes our collective imagination and impacts support for scientific research. Effective education and thoughtful analogies play pivotal roles in bridging the gap between complex cosmological ideas and everyday understanding, while cultural narratives shape how these cosmic truths integrate into the human story. From classrooms to popular media, conveying the nature of the universe's expansion requires careful attention to language and imagery. Concepts like metric expansion of space can appear esoteric and counterintuitive, especially given that expansion defies everyday experience. Therefore, educators often employ analogies such as the balloon and raisin bread models to provide accessible entry points. These metaphors, while limited, effectively convey critical ideas. Galaxies moving apart, not because they are flying through space, but because space itself stretches. However, educators bear the responsibility to clarify the analogy's limits. Misinterpretations, like envisioning a cosmic center or imagining the universe expanding into a pre-existing void, are common. Pedagogical materials increasingly emphasize the importance of precise explanations alongside engaging visuals to prevent misconceptions and foster deeper conceptual grasp. Technology advances have expanded how education reaches audiences. Interactive simulations, virtual reality experiences, and dynamic visualizations allow learners to explore cosmic expansion actively, manipulating parameters to witness how galaxies recede or how light stretches through expanding space. This experiential learning dramatically enhances comprehension and retention. In popular culture, cosmological themes resonate deeply. Films, books, and art exploring the infinite cosmos tap into a fundamental human fascination with origins and destiny. Works like Carl Sagan's Cosmos series or contemporary documentaries provide narratives that blend scientific accuracy with poetic wonder, inspiring curiosity and reverence. Such cultural touchstones contribute to a shared cosmic literacy that transcends scientific circles. Moreover, public understanding shapes policy and funding for fundamental research. When society appreciates the grandeur and significance of cosmic discoveries, there is greater impetus to support missions that probe cosmic microwave background radiation, launch space telescopes, or investigate dark energy. Outreach thus fuels science itself, creating a virtuous cycle. Yet, challenges persist. The immense scale and abstract nature of cosmology demand ongoing effort to nurture scientific literacy. Tailored approaches, considering diverse educational backgrounds and cultural contexts, are necessary to make these lofty ideas inclusive and comprehensible. Ultimately, the cultural impact of understanding the universe's expansion touches philosophical and existential realms. It reframes humanity's place in the cosmos, inspiring humility while fueling imagination and scientific inquiry. The narrative that the universe is dynamic, expansive, and ever-evolving enriches human culture, inviting us all to behold the cosmos as an endless frontier. As we continue exploring cosmic mysteries, education and cultural dialogues remain paramount. They empower us not only to grasp the universe's physical realities, but also to find meaning in our shared existence within this vast and expanding tapestry. As we survey the vast landscape of cosmological knowledge, we recognize that despite the remarkable progress of the last century, profound mysteries and open questions continue to challenge and inspire physicists and astronomers. The frontiers of research in cosmology are vibrant arenas where theory meets observation, where new data opens doors to unexpected insights, and where the quest to comprehend the universe's expansion continues to push the limits of human understanding. One major open question revolves around the fundamental nature of dark energy, the enigmatic force driving the accelerated expansion of the universe. Is it truly a cosmological constant, an intrinsic vacuum energy of space? Or does it arise from a dynamic field evolving over cosmic time? Resolving this mystery has monumental consequences for physics, as it could require modifications of Einstein's general relativity or usher in new physics beyond the standard model. Upcoming missions, such as the Euclid satellite and the Nancy Grace Roman Space Telescope, aim to map dark energy's effects with unprecedented precision by measuring galaxy distributions, gravitational lensing, and supernova distances. Closely intertwined is the nature of dark matter, which composes roughly 27% of the universe's energy budget and influences cosmic structure formation. Although its gravitational effects are well established, dark matter's particle identity remains elusive. Experiments in underground laboratories, high-energy particle colliders, and astronomical observations work in tandem to detect or constrain candidate particles and their interactions. Another frontier involves probing the earliest moments of the universe, particularly the inflationary epoch, a rapid expansion phase that smoothed and flattened the cosmos, sowing seeds for galaxy formation. Detecting primordial gravitational waves in the cosmic microwave background, polarization patterns could confirm inflation models and unlock details about physics near the Planck scale. Projects like BICEP and the Simons Observatory are at the forefront of this search. Advancements in gravitational wave astronomy open new vistas. Observations of merging black holes and neutron stars provide novel probes of spacetime, test general relativity under extreme conditions, and offer glimpses into early universe phenomena inaccessible via electromagnetic signals. Challenges persist in understanding the so-called Hubble tension, the discrepancy between locally measured expansion rates and values inferred from early universe observations. This tension hints either at unrecognized systematic errors or new physics affecting cosmic expansion or energy components. Theoretical physics continues to explore broader frameworks, including quantum gravity, string theory, and the multiverse hypothesis. These ambitious endeavors seek to unify quantum mechanics and gravity, explain the emergence of spacetime itself, and contextualize our universe within possibly richer, higher-dimensional realities. However, connecting these theories with empirical data remains a formidable task. Additionally, the nature of time, causality, and the global topology of the universe remain subjects of intense inquiry, blending physics with philosophy. Understanding whether the universe is finite or infinite, how it might be closed or open, and whether it possesses structures beyond our current horizons continues to provoke debate. As observational technology advances, through more powerful telescopes, more sensitive detectors, and innovative analysis techniques, cosmologists aspire to chart the universe's history with greater fidelity, unravel dark energy's essence, detect primordial signals, and test new hypotheses. In parallel, interdisciplinary collaboration between theoreticians, observers, experimentalists, and philosophers fosters a dynamic scientific culture where ideas are tested, refined, and sometimes revolutionized. The path ahead is as challenging as it is exciting, a journey into the unknown where each discovery deepens the mystery and enriches our cosmic narrative. The universe's expansion, once a startling revelation, now stands as an entry point to vast intellectual frontiers that beckon human curiosity and ingenuity. As we prepare for the concluding reflections, this frontier spirit reminds us that the quest to grasp the vastness of the cosmos is not only about understanding physical phenomena, but also about exploring the limits of knowledge and embracing the profound wonder that defines our place in the universe. As we draw this extensive exploration to a close, it is fitting to reflect on the profound journey that humanity has undertaken to grasp the universe's vastness, a journey marked by curiosity, perseverance, and a relentless drive to understand our place in the cosmos. From ancient stargazers crafting myths to modern scientists probing the cosmic microwave background, the quest to comprehend the universe's expansion symbolizes both scientific triumph and a testament to human imagination. Our beginnings were humble. Early humans looked upward and saw patterns in the night sky, attempting to weave their observations into coherent narratives. These early cosmologies, though distant from scientific rigor, laid the cultural foundation for curiosity about the heavens. Over millennia, thinkers transformed these myths into systematic philosophies, challenging Earth-centered views and conceiving new cosmic architectures. The advent of modern astronomy sparked revolutions: Copernicus's heliocentrism, Newton's laws, and Einstein's relativity that refined our understanding of space and time, revealing a universe not static but dynamic. Edwin Hubble's discovery of cosmic expansion reframed the very fabric of reality, compelling a re-evaluation of existence on the grandest scales. Contemplating the universe's expansion invokes concepts that challenge intuition: the stretching of space itself, the cosmic horizon beyond which light has yet to reach, the enigmatic dark energy accelerating the cosmic swell, and the possibility of dimensions and universes beyond our perception. Such notions stretch both mathematical sophistication and philosophical depth. Yet this quest is not solely the province of science. It straddles philosophy, encouraging us to ponder infinity, the nature of time, causality, and the essence of being. It inspires art, culture, and our collective imagination, reminding us of both our insignificance in the cosmic scale and our unique capacity to contemplate the cosmos. The endeavor to understand the universe's vastness paints an ever-expanding picture not only of space and time, but of human aspiration. It highlights our desire to reach beyond, to know the unknown, to connect the stars with our own searches for meaning. As our instruments refine and our theories evolve, the cosmos will continue to reveal new secrets and pose fresh questions. The boundless universe, expanding forever into the unknown, mirrors our unending quest for knowledge, ever unfolding, ever challenging, and ever inviting us to marvel and explore. In the vast darkness, beneath the glittering tapestry of stars, humanity's understanding flickers and grows, a light that honors both our origins and our destiny within the infinite expanse.